Hi, in this video we're going to be solving an example problem related to finding the moment around a specified axis, the moment caused by a force F. So here we have force F, and we're going to be asking how to find the moment caused by this force F around axis x-axis. Right, so let's write down the question here. So we have a sleeve here. So this is called a sleeve. The blue thing is called a sleeve, so we have the sleeve. The friction at sleeve A so this is sleeve A, and we have the sleeve here. Okay, let's highlight this sleeve at point A. Okay, so what about the friction at the sleeve A? So that this friction can provide a maximum resisting moment, resisting moment of 125 Newton meters, and that's about the x-axis. Okay, so 125 Newton meters is the maximum resisting moment that can be applied at sleeve A. Okay, so the question is determine the largest and magnitude of force F that can be applied to the bracket, so that the bracket will not turn. So we don't want this bracket. So this is my bracket that I'm highlighting right now. So this bracket under this force F has a tendency to rotate around x-axis. So that is like rotation around x-axis. So we don't want that rotation happening, and what's preventing that rotation is the friction. So this friction is preventing that rotation, but there is a limit, of course. So there is a resisting moment that this friction can be overcome, the maximum moment. So that's 125 Newton meter for this particular sleeve at A. So for the solution, essentially we're trying to find, so we will actually find the applied moment. So we have the resisting moment 125 here, and we need to find the applied moment around x-axis, and that's due to force F. So that's what we want to do. Okay, so for that we need to first of all find moment we can find moment AB. I'm sorry, so just let me check. Okay, so just what we want to do here is to find a moment about an axis, and I just want to add here just to remember the theory. Sorry about that. Oh, I'm not able to add the copy and paste the figure here. I think that's happening because I'm recording right now, but I will just try once again. Okay, that's it. So this is what I wanted to show you guys. This explains many things actually. So here, recall. Okay, so we have this force F here. So this force F here, and so what we want to do on this particular figure, we want to find moment around A axis caused by force F. So what we do is to find, first of all, a moment caused by F on any point lying on the A axis. So we are, okay, use the right pen here. So moment about point O is actually this. We use this position vector R. So position vector R cross product F. Okay, so this is MO, R times F. So what we essentially do is to project this MO vector onto AA axis to get a moment A. So, and that's done by a dot product. So moment A, so dot product yields a, so that's a vector, by the way. Okay, so dot product will be a unit vector written along the A axis. So that's dot product R cross product F. Okay, and that will give me a scalar value for moment A. So that we recall this. Okay. So now, as for the solution of our problem, what we want to do is essentially, if I may copy and paste this here, hopefully I will succeed. Okay, I think I'm successful with that. And right, so what I want to do here is to just use a thicker pen here. Okay, so I have my point A lying on the x-axis. So how about finding a position vector RAB, and then this force vector F, right? And then okay, and then I can here find a moment around point A will be equal to RAB cross product force F. And then the second stage, so the second step will be to find MX. So MX will be so this will be I, which is the unit vector, so that's unit vector along the global x-axis, right? So that's the unit vector for x-axis. So that's what we all know that. So that's dot product RAB cross product F, right? So this is our formula to find mx. We need to calculate all these RAB, F, and I, and then dot product and all that, right? So let's keep on with the solution then. So what I want to find is actually, first of all, RAB. So, okay, here. So RAB vector will be equal to, I'm going to just write down, so that we have this along x-axis, this point up here is 150 millimeters away from the origin along the x-axis, up 100 millimeters along the z-axis, and along the y-axis I'm having a 300 millimeter. So it's easy, it's very straightforward to write this RAB vector. So that will be for the x it's minus, so here it's minus. So I'm having my minus in meters 15, so that's minus 0. So that's the coordinate for B, and that's the coordinate for point A. Okay, so basically let's just write down. So coordinates for A will be 0.0.0, and coordinates for B will be minus 0, 15, and 0.15, 0.3 for Y, and 0.1 for Z. So this is basically what I'm trying to do. So that's I, and plus 0.3 minus 0J, and plus 0.1 minus 0K. So RAB vector will be equal to minus 0.15 I plus 0.3 J plus 0.1 K. Okay, so that's my RAB here. RAB is found. As for the force vector, so my force vector will be equal to, okay guys, just try to remember how to write a vector as a Cartesian vector. So I'm given here, let's just highlight with red, the direction angles. So for I'm given like the angle of force vector F with the x-axis is 60, with the y-axis is 60 again, and with the z-axis, so that's the z-axis angle, that's 45. So 60, 60, and 45 for x, y, z axis respectively. So I know that I can write a vector with these given angles, and by multiplying f with the unit vector actually. So that's the unit vector for my f, and that's f times, and that's cosine 60, and that's I plus cosine 60 at the y-axis, so j plus cosine 45 k. Okay, so So this is how I write my force vector. Okay, right. Oh, I just made one mistake here, so that for x that should be minus. Okay, so this should be minus because it's the x component of f is pointing towards the negative x-axis, so that's why this should be negative cosine 60i. Right. So if you calculate that, I can finally write the 0.5 f I a minus 0.5 plus 0.5 f and then j and plus cosine 45 0.707 f k. Oops, sorry. I'm sorry. Okay, so this is my force vector here. Right. So I need to now do the multiplication, dot product multiplication. So mx, moment x, is equal to I dot product RAB cross product f vector. So that's my RAB and that's my f vector. So this can be written as the determinant of some numbers. Okay, so this matrix includes the first row will include my unit vector component, so that's for x it's 1, for y it's 0, and for z it's 0. And then components of RAB is the second row, so that's minus 0.15, 0.3, and 0.1. And for the f 0.5 f and 0.5 f and then 0.707 f. Okay, so I will not spend time remembering how to do this operation here, or just will write the result for you guys. So I is like 1, so 1, and then in square brackets 0.3 times 0.707 f minus 0.5 f times 0.1 right, and then plus 0 plus 0. Okay, so you will remember how this is done. So there's a practical rule for that. So I end up with 0.162 f. Okay, so just let's wrap it up. Let's wrap it up here. So I'm having, as a result, a moment around x-axis by force F is equal to 0.162 f. Right. So let's go up and remember what the question is asking. Oh, sorry. Oh my god. Anyway, I'm having this problem here. Okay. Sorry about that. Okay. Let's go up. Let's go up. Okay, so the question is asking the friction at sleeve A. So the moment capacity is 125 moment capacity. So what is F then? That can be applied such that the bracket will not turn. Okay. So I'm going down here now. This has been a long solution now, I guess. So here I will substitute for mx the capacity 125 Newton meter, and that will be equal to 0.162 F. And from here I will be having F is equal to 771 newtons, and that's my force that can be applied on that sleeve, such that the maximum force that can be applied on that sleeve that prevents friction occurring. Okay, so if you apply a value greater than 771, there will be like a rotation around that sleeve, because it would be exceeding the capacity that is moment capacity that is produced by the friction over there. Okay, so this concludes the solution of our problem. Thank you for listening.